This is it's after the last week's seminar, tutorial seminar, and today's talking in the research overview of chiral science in how to want to do in the future. Anyway, resume. No, not to moving. Okay, now. We have to remember the last time I tell you the last week with chiral magnet, what we find in the chiral magnet. Here is a list of the important feature of chiral magnet. The first one is crystal chirality and the spin chirality are strongly coupled via DMI, gelatin schema interaction. And the other one important thing is stabilization of coherent spin phase order. It is possible to coherent phase order for magnetic, electric, and dipole and quadrupole magnetic phase order also we found. And the third one is generation of topological phase defect. It is a spin case. We already shown before, chiral spin soliton and the skyrmions, and etc. The fourth one important things is emergence of nonlinear properties. We can find nonlinear magnetic susceptibilities, and we can find the electric nonlinear susceptibilities in the chiral system. And now let's go further. Here, I already tell you before, just the chirality is shape chirality and motion chirality. Motion chirality is angular momentum. It corresponds to the spin angular momentum. And the shape chirality is crystal chirality and molecular chirality. Let's consider, we can consider to the quantum chirality, this case. Let's to move the further smaller world. Now, here is we find the spin chirality and the crystal chirality is already joined. And we can go more smaller world and more bigger world for the chiral system. And this chirality, we can consider the scale-free feature. Then we can possible to common system on from the small world to huge world. And our chiral magnet already tell you the chirality can spread by itself, by crystal chirality to spin chirality, and we can expect this spread is more bigger or smaller one. Let's remember the go back last seminar. We synthesize many different chiral magnet from the molecule-based system and the inorganic system and intermetallic compound also. Let's remember the system of inorganic chiral magnet system. I already tell you the last time. The spin can influence by the crystal chirality and to make a very huge helix, spin helix. And the helicity of this system is coming from the crystal chirality. Then if we make the single enantiomeric crystal, our system is only one side helicity they have. Then this case, we can make a spin coherent system, and we can generate the spin soliton system by applying magnetic field. At the zero magnetic field, their helicity, they make the chiral helix system. And if we apply the magnetic field, we can control the width of soliton and generate a soliton. And this is we can calculate by the analytically by using the Hamiltonian, and this case is very good for the experimental data. And today we have to go further, and this is a video increasing magnetic field perpendicularly to helical axis. The pitch of helix, and this is the width of solitons is very smoothly we can control by the magnetic field. Then now we have to go further. And there are two things we have to consider. As already known, this is a CP spontaneous breaking of the fundamental particle. And this one is the structural chirality, geometrical chirality. When we consider the electric spin, angular momentum, and the magnetic moment, if the plus spin angular momentum they have, the magnetic moment appear to up. And if the opposite sign, spin angular momentum, the magnetic moment go down. If we consider CP spontaneous breaking of this electron system, this case is a plus spin angular momentum. Minus spin angular momentum. They generate magnetic moment up, but charge becomes plus. Then C is a charge, and P is parity. Then charge and parity breaking means we have to the charge becomes opposite. But my plus spin angular momentum for positron, the magnetic moment go down. It is looking very similar of the right screw and left screw, but we don't know. This is not the same. Then we have to consider the more deeply about CP violation and the chiral system. But this is a phase diagram of our chiral magnet. I already said before, all chiral magnet has a very similar properties, and the phase diagram is almost same. And this is a phase diagram of chromium niobium sulfur compound. At a high temperature, they are paramagnetic. It is no problem. And at the TC, it's 130 Kelvin. They are going to the helical magnetic structure. They are long range order to chiral helix state. And if we apply the magnetic field perpendicularly on this compound, they are going to the chiral spin soliton system, lattice state, and finally they are going to forced ferromagnetic state. And this dashed line is not phase boundary. Sorry, this is just for eyes. But anyway, here, this line is second order magnetic long range order boundary. And here is the first order transition line. In this case, we have the three critical point around here from the second order to first order. And here is a paramagnetic and the fourth ferromagnetic line is we can measurable by the magnetic measurement. And this green is nonlinear magnetic susceptibility. It's 3 omega nonlinear response here. Here at just above of TC, there is, I already said before, very strong 3 omega response here. Only this zero field. If we apply magnetic field, this nonlinear susceptibility disappear, and at around 1000 Elsted, the nonlinear susceptibility appears again. This line is like this. But we can say this is paramagnetic, and this is a chiral soliton lattice, and this is the coexisting phase, soliton and the ferromagnetic part. They have the domain structure, and this is the fourth ferromagnetic state. This is easy to understand by using our Hamiltonian. This is already said you before. This is our chiral spin system Hamiltonian. Here is exchange interaction between spins. Exchange and dipole is same. And here is Jalashinsky-Moriya interaction coming from the chiral crystal. And this one is a Zeeman term. This is outer applying magnetic field. Then if we apply magnetic field perpendicularly strongly, they are going to become, this term is very strong, then they are going to force the ferromagnetic state. But between them, the chiral spin system is stabilized. And eventually, we know the QCD people also find similar Hamiltonian. This one is QCD theoretical Hamiltonian. Mathematically, these are same. This is the same as the interaction between particles, and here is a chiral anomaly term is the same mathematics, and the quark mass term is also same. Then we can compare with QCD world and the spin chirality system. Then here is this is I already said our phase diagram, and QCD people are also considering very similar phase diagram. But as you compare the scale of the temperature and the density is completely different. Our system is 100 Kelvin, but their system is 10 to 12 Kelvin. It's much different scale. And the density term is also completely different. We are the soliton density is here by applying magnetic field, and their baryon density is like this. This one is the density of nuclear of the atom. It is very dense. Already the one is very dense, and the 4 is incredibly dense system. It corresponds to the core of neutron stars. But the QCD people already tried to do the experimentally this system. Very recently, the Alice group is the Shigaki sensei is a member of Alice group. They did this experimental. They doing the collision of red nucleus at the very close to the light speed. There are two nucleus of red, and they make a collision. Almost 99.99999% of with light speed. And then they are going to, from this nuclear density to heating up this temperature. And they find they lost hadron phase to the QGP phase. This is correspond to the they lost this term, and they are increasing much bigger this term. Then they are going to the like a paramagnetic state. This is correspond to us spin system is same. If we increase the temperature, the spin system becomes very temperature energy is much higher than the exchange interaction. They are going to paramagnetic phase. The same with this one. And here they thought something the coexisting phase exists here. This is a first order transition line, and this one is second order transition line. This is same with our system. Then just recently we published by the theoretical inspection of the this line by this paper. What we did, maybe it is possible to observe the like a spin soliton system. This is a paper, and what we did, if we collision doing the offset collision, they generate like a soliton lattice, like this for the Z direction, Z direction. Then if we extract data from the collision data, maybe we can find some soliton generation of this energy. Then this is just first paper we publish, but anyway, in future, we can do many things. For instance, this low temperature and high density region, they expect the color superconductivity phase. But if we do the experimentally, it is almost impossible to arrive this density. But our chiral magnet, it is possible to measure directly this structure. We already find some new phase in our chiral magnet. Today, in later, in maybe Wednesday or Thursday, Javier Campo will come, and he gave a lecture by the neutron diffraction in this phase and muon mu-SR measurement observation of this phase. And we can reach to this toric critical point using our system to QCD system. The other future plan is just go back from this page. This is I said to you the last week. There are anomalous properties in surface or interface, and here is breaking symmetry of crystals or material. This is a cycle, and periodicity is coming from the Leonardo Fibonacci series, and Roger Penrose, considering of the uh, this asymmetry tiles, so-called Penrose tile. He got a Nobel Prize recently. And Dan Schichtman find experimentally by the pseudocrystal. He got also Nobel Prize in chemistry in the 2010. But let's consider the crystal symmetry and this asymmetry. This is our data. We synthesized this kind of chiral magnet before, long time ago, in 2004. This crystal contains this triple strand helix inside. Let's consider this one. This system, we are lucky to grow the crystal for enantiomeric pure chiral crystal, and also the racemic crystal, the same component. This magnet contains manganese 2 and chromium 3 and cyanide bleached, and we add the amino alanine, it's amino acid derivatives, using the chiral enantiomeric pure and the racemic also. And the chiral one and the racemic one is different structure. Let's to see the structure. This is the chiral one. Here we can find the chromium and the manganese and the cyanide bridges, and they makes a helix, only one side helix. If we use a left-handed amino alanine, our helix is left-handed chiral helix here. And here is a triple strand helix, I already said before. And this helix, left-handed helix, is same with this one is left-handed and left-handed. Yeah. This rectangular helix is same chirality. Then if we look the racemic one, it's like this. The helix is same. It's made by the chromium and the manganese cyanide bridge. But the helicity is, this one is left-handed, but this helix is right-handed. It's fused. Left-handed and right-handed are left-handed and right-handed. Why? Possible. But this one is easy to consider. If we put the same chiral helix, make a structure using the same chiral helix, this case, we can share only the corner. Then we cannot share line, but we can share only corner. Then makes this kind of motif. But if we put the right-handed and left-handed helix, they can share line. Then the density becomes heavier, and the cohesive energy or crystal energy is different with chiral form and the racemic form. Then let's to see the magnetic ordering temperature for both. This chiral one is magnetic transition temperature is 35 Kelvin, but racemic one is 53 Kelvin. This magnetic ordering temperature is correspond to the like a crystal energy, but the spin system energy. There, the exchange interaction between the spins, racemic form is much stronger than the chiral form. This is, we can consider the crystal energy also different. Then we can say the racemic crystal is more dense and they get a more big coercive energy or like a crystal energy than the chiral enantiomeric one. And then if we consider again this smoothly changing by magnetic field, our helix can control by the magnetic field, and their motion is very, very smooth, like a very, very elastic system. And there are no defect we find. Then we can consider about this one. This is a picture of our food, pudding and cognac and jams. They made chiral polymeric molecules. And then now let's consider our system is a spin-spin or magnetic interaction system is this Hamiltonian. And if we consider the strong force system is same Hamiltonian we find. Then this case, there are no depend on the force origin. Spin-spin force interaction or strong force interaction are same. Why we cannot consider about the chemical bond and the hydrogen bond within the protein or sugar polymers? Let's think more further. Our protein made by the one side, one chirality, 100ness of amino acid, and their structure is made by the chemical bond and hydrogen bond and the other energy, dipole energy or dielectric force. This is just previous Danis lecture. Yes, he said more detail. But anyway, then we can consider more further. This is age-related disease. One of age-related disease is Alzheimer's disease. This Alzheimer's disease and mad cow disease is the origin or the reason is getting the amyloid beta protein or abnormal prion protein. The common structure of this protein is similar, and the right-handed alpha helix and the left-handed, it's looking like the nitrogen end and the carbon end is opposite. Then they connect to the racemic helix pair, and they aggregate racemic helix, and they get more big crystal energy or coercive energy, which I experimentally explain. But if we consider like this, they get a big coercive energy, and they can grow itself like a crystal. Then this is the reason maybe, but this is not easy. The Alzheimer's disease, we need a tau protein aggregation, but tau protein is very similar, very huge cohesive energy they have. They are automatically going to crystallize, and then we have a problem. The other case is already our colleague already find in the cataract case is also similar. The one of our proteins that is uh, the what arginine, not arginine, some amino acid possible to racemize at our body temperature, and they are racemized by time. It corresponds to age. There becomes the homochirality is becomes collapse by time, and this the crystalline protein makes aggregate, and there becomes a real crystallized in the eyes. Then we have a cataract disease. But this is possible to consider our aging is we can consider by this case. The by aging, in a polymeric protein amino acid, they are automatically going to racemize by age at our body temperature. And then the concentration of this amino acid inside in the protein, their concentration increasing by time. Then maybe possible to consider by the aging is coming from the collapse of homochirality. Then now we are already start our collaboration team by this is a skin aging team. These are mainly our member, Tate Sensei and Danisu is the previous speaker, and the other specialist for the research of the amino acid and the chiral plasmon person and the analysis of the amino acid and the synchrotron. He's Professor Matsuo from our high soul and the separating person. But anyway, now we have our human skin of the baby and the middle age and all the persons real human skin given by our collaborator from Kyushu and Kumamoto University. And then we start to analyze these human skins and doing the get the peptide and analyze chirality by using different techniques. But anyway, I have still time. We can summarize here. Our chiral world spread, possible to spread quantum chirality to biomolecular chirality. And then I have a time left to talk about our complete different but interesting results. This is the study about chiral crystal design using AI. These are our member of the deep learning research. Then we applied the chiral crystal design is still difficult nowadays. Then it's better to expect by the or using the deep learning. This is just what is deep learning. Maybe you already know. We get a snapshot, many snapshots of the different crystal system, and then we put the deep learning on the result and the snapshots. We did this kind of things. This is okay. How to evaluate the data? We use a logistic regression for the snapshot and the crystal space group. Yeah, this one is the number of the teaching data is 1,000, and how the space group converge to this one. Then we did. This one is the group number of the periodic table, and this one is A and B, AB type crystal. AB means that, for instance, NaCl is Na is A and Cl is B. Then the two different element compound. Start from zero group, group 1 to 17. The halogen is here, and this one is alkali metal. This is for A, and this is for B. The first trial get the probability of chiral crystal. Red is high, and blue is low. As you can see here, there are not line symmetry here. We should have the line symmetry here, but it's not asymmetric. Then this is not very good. Then we spread more deep learning using the multi-layer system. Here is the input of snapshot, and we get the space group here. And we have some layers using some coefficient of the equation. Then this is the number of teacher data. It's 10,000 teacher data. And here is accuracy to get the chiral crystal. If we increase the number of teacher data to 10,000, finally we get 73%. We can expect chiral or non-chiral. It's central symmetry. We're using the more than 1,000 case. This is a result. Same number of group number is here, 1 to 18, but 70, of course. And then the red one is probability is chiral crystal is increasing. Red one. For instance, manganese silicide is here, is high chiral probability of the crystal, and the manganese phosphate is here. Then this is something looking like very good. But now we can spread to 3 different systems. Is A, B, C system. We can do by this deep learning. It is easier. This is a slice of the different groups of C. For instance, C is 5 groups is this one, and 8 groups is this one, is 9, like this. This one is 14 group, 15 group of 15. Then, no, there are nothing data, but anyway, I'll tell you. For instance, chromium, niobium, sulfur is something here. Sulfur is 16, no. I said that the chiral magnet is something here. And I didn't tell you, but we find the other chiral magnet is coming here. But anyway, if we use the deep learning system, we can choose the element to get the chiral crystal using this. But anyway, the deep learning system is possible to use chiral crystal design. Now the almost time, and then let's go into summary. But our findings, I said last week, we did the chirality is changing the topological phase transition. They make a defect, like solitons or nodes or skyrmions using, we are researching this branch. Yeah. But now we can spread to the quantum chirality here, QCD system, and the biological system, this branch, and this branch maybe. But anyway, the chirality is possible to spread many different scales. Then this is summary, and I have to acknowledge many people with theoretical people and the spin chirality system measurement person and the synthesis people and the nonlinear susceptibility people and the high field and low temperature measurement system and the neutron diffraction members and the Lorentz stem people and the QCD measurement, QCD persons. And the other, the collaborators with the Crescent team is Chirality Research Center team. These people are members of our team. Now then, thank you very much for your kind attention.